All right, let's just jump right in. Prime numbers. You know them, right? 2, 3, 5, 7, 11. They're like the atoms of the number world, the building blocks for everything else. But man, they seem to pop up with absolutely no rhyme or reason. For centuries, mathematicians have been hunting for some kind of order in all that chaos. Well, today we're going to look at a really cool twist in that search. So here's the million-dollar question. Are they really random? I mean, when you look at a list of primes just stretching out forever, it feels totally unpredictable. But in math, what looks like pure chaos on the surface, well, sometimes it's hiding something much, much deeper. And there's a good reason they're called the most fundamental and, yeah, the most complicated objects in all of mathematics. But what if that's not the whole story? What if, just beneath all that noise, there's a hidden rhythm? A faint pulse of order just waiting to be found. So we're diving into patterns in prime chaos, the search for order. And to find this rhythm, we have to know what we're looking for, right? We're not talking about some simple formula that just spits out the next prime number. No. The search is for something a little more elegant, a special kind of sequence called an arithmetic progression. So what in the world is an arithmetic progression? It's actually super simple. Think of it like a drum beat. A steady, constant rhythm. You pick a starting number, and then you just add the exact same amount over and over and over. That amount you keep adding, that's what we call the common difference. And here are a few examples to make it crystal clear. Look at that first row. You start at 1, you add 2, you get 3. Add 2 again, you get 5, and so on. Or the second one, you start at 8 and just keep subtracting 3. It's this really beautiful, simple, additive pattern. And that is what mathematicians were hoping to find hiding somewhere in the wild world of prime numbers. Which brings us to a truly monumental discovery, the Green-Tau theorem. I mean, this wasn't just some small step forward. This was a giant leap from math kind. Two mathematicians, Ben Green and Terence Tao, they took on this massive question, and what they found was just stunning. The theorem basically says this. The primes contain arbitrarily long arithmetic progressions. And what that means is absolutely staggering. Think of any length you want. A sequence of 5 primes, 50 primes, 1,000,000 primes, all perfectly spaced apart. The theorem guarantees that sequence exists, somewhere out there in the infinite list of primes. It's there. We just have to be able to find it. And this is why it's so mind-blowing. Primes are by their very nature multiplicative, right? They're all about what you can and can't divide them by. But arithmetic progressions are purely additive. They're about adding the same thing over and over. So finding this perfect additive pattern inside a multiplicative world, I mean, that's like finding a beautiful handwritten poem tucked inside the source code of a computer program. It's a connection that just shouldn't be there, but it is. But the proof for this thing? Oh man, it was an absolute epic. We're talking 60 pages, and not 60 easy pages, 60 pages of some of the most dense, complex math you can imagine. It's a total masterpiece, for sure, but it's also a Goliath. It's so tough to get through, and that very complexity is what led another mathematician to ask a really, really clever question. So now we get to this clever twist, finding almost perfect patterns. The idea was, what if we just tweak the goal a little bit? Instead of hunting for a perfect pattern, what if we settle for one that's just almost perfect? And this is the real game changer. What if we don't need a perfect pattern? What if we look for one that's just close? What if we could find a string of prime numbers that gets arbitrarily close to one of these perfect progressions? The spacing wouldn't be exact, but the little errors, the wobble and the pattern, we can make that wobble as tiny as we want. And this really lays it all out. On one hand, you've got the Green-Tau theorem, the Goliath, finding perfect patterns with that monster 60-page proof. On the other hand, you have this almost theorem, which just gets arbitrarily close to the patterns. And the result? The proof isn't an epic novel. It's a straightforward 3-step argument. It's a huge simplification, and all we had to do was relax the rules just a tiny bit. Okay, so this visual is perfect for understanding what getting arbitrarily close actually looks like. See that top row? The dots are kind of scattered. They're around where a perfect line would be, but not quite. Now as you move down, you see the approximation getting better and better. The points are tightening up, getting closer to the ideal. By the bottom, it's almost impossible to tell the difference from a perfect one. This almost theorem proves you can always find primes that do this. They get closer and closer, for any length you want. So how in the world does this super simple proof actually work? It's beautiful, really. It's not about brute force calculation. It's a clean, logical chain of 3 simple steps. It's all about understanding what prime numbers are at their core. So here's the game plan in just 3 steps. Step 1, we show that the primes are dense. Step 2, we show that being dense means they have to be everywhere. And step 3, we show that being everywhere guarantees you'll get close to these patterns. Dense to everywhere to closeness. Let's walk through it. All right, step 1. The primes are dense. How do we know? Well, there's this classic result from Euler. He said, what happens if you take the reciprocal of every single prime number, so 1/2 plus 1/3 plus 1/5 and so on, and add them all up? You might think they'd add up to a nice, neat number, but they don't. The sum just keeps growing forever towards infinity. And that tells us something huge. Primes aren't rare. There are so many of them that their combined influence is literally infinite. Okay, so that brings us to step 2. If their collective influence is infinite, what does that mean? It means they have to be, well, everywhere. This infinite density guarantees it. Think about it. You just can't have these vast, empty deserts along the number line with no primes in them. They have to keep popping up all over the place, no matter how far out you go. And here's the beautiful final piece of the puzzle, step 3. It turns out there's a mathematical rule that says any set of numbers that has this everywhere property is forced, it's guaranteed to get arbitrarily close to these long arithmetic patterns. And since we just showed the primes are everywhere, well, the conclusion is inescapable. They must have these almost perfect patterns. It's baked into their very nature. So why does any of this almost stuff matter? I mean, is it just a clever shortcut around a hard proof? No, not at all. The real value here is so much deeper than just making the math shorter. It actually gives us a whole new way to think about the problem. Yeah, the author of this paper, J.M. Fraser, he put it perfectly. He said, the simple proof gives, quote, a heuristic explanation of why the primes possess arithmetic structure. It's not just a proof that it's true, it's an explanation for why it's true. It gives you a gut feeling, an intuition for why these patterns have to exist. It's because they're so dense. So let's just boil it down. This almost proof is a big deal for a few key reasons. First, it gives us that intuition, that feel for the hidden structure of primes. Second, it actually connects to one of the biggest unsolved problems in this area of math, the Erdős-Turan conjecture. And finally, it's just a fantastic example of creative problem solving. It shows how just reframing the question can turn a monster of a problem into something, well, something elegant. It really makes you think, doesn't it? We just had to change our definition of perfect by a tiny little bit, and suddenly we unlocked this deeper, more intuitive truth. So it leaves you with this question. What other almost perfect patterns are hiding right there in plain sight? Not just in math, but anywhere. What are we missing just because we're so obsessed with finding absolute perfection?